Hi, my name is Julia Vitale, and this is Physics 2 Lab 4, Magnetic Field of a Bar Magnet. Here's just a brief overview of everything I'll be talking about today. So the primary goal of this experiment was to determine how the magnetic field of a bar magnet depends on distance. I compared our physical measurements to theoretical predictions for both on-axis and off-axis magnetic dipole fields. So key results from my analysis included a calculated magnetic dipole of 1.968 Newton meters per Tesla and a distance-dependent slope, or N, of negative 3.0499. So to understand my data, I relied on several core physics concepts. So I used the Biot-Savart law and the general formula for the magnetic field of a dipole. And then for the distance dependence analysis, I used the formula B bar equals K R of N. And then by taking the natural log of both sides, we can convert this into a linear equation where N would represent the slope of the experimental line. So the procedure began by orienting my smartphone to align with Earth's magnetic north-south axis to minimize the interference, and then I identified the precise location of the magnetometer sensor inside the phone and positioned the bar magnet on a meter stick and recorded field magnitudes at various distances. And then for the off-axis part of the lab, I moved the phone both horizontally and vertically to measure the field at a 45-degree angle to correct for Earth's background field in the final calculations. So here you can see the data collected for the on-axis measurements. So by plotting ln bx against ln r, I generated a linear regression, and then the resulting equation right here provided us with the slope right here, which is negative 3.0499. That will be used in the calculations on the next slide. So by also using the y-intercept from the graph, which was negative 14.748, I was able to solve for k. And then from there, I was able to solve and calculate the magnetic moment to be approximately 1.968 nanometers per Tesla. And then for the off-axis experiment, I measured the field at an average perpendicular distance of 0.1717 meters, and then after correcting for Earth's magnetic field, I determined the net magnetic field at this 45-degree location. So I then created a computational model using starter code in VPython to visualize these fields. So essentially in this code, it's defining a function for the dipole field and creating arrows to represent the field at different observation locations, 2 on axis and 4 perpendicular to the axis. And then the model essentially is predicting a magnetic field magnitude of 2.16205 e to the negative 5, which in comparison to the computational model is obviously different. And as you can see here, these are all the lines, and then this is, or all the vectors, and then this is the 45-degree line. So here are a few assumptions and possible errors that could have been made. So in this lab, I assumed that the bar magnet acted as a perfect magnetic dipole and that the field falls off predictably as distance increases. And then there also were potential errors that may have occurred, such as electronic devices or other magnetic objects near the setup that could have skewed the magnetometer data, and the exact location of the sensor chip inside the phone may not have been perfectly identified. And then these are my observations and what I noticed. So the 2 ones that I said were true were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And then as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And then for the other 2, I said they were false according to my observations. So then these are the answers to my 2 discussion questions. So for the 2 discussion questions. So for the first one, essentially if the meter stick was at an intermediate angle, Earth's field would contribute to the BX readings, and then this would mess up the magnet's data with Earth's horizontal component, shifting the entire y-intercept of the graph and then leading to an incorrect calculation of the magnetic moment. And then if we had stuck 2 identical magnets together, it would approximately double the total magnetic dipole moment. And then while the direction would still remain the same, the magnitude of the magnetic field at any distance would nearly double, which makes sense of due to the parallel magnetic dipole relationship. Thank you.